talk, I'm going to present some results of a recent study indicating that network-wide thermodynamic constraints shape the specificity of metabolic redox reactions with respect to the redox cofactors NAD and NADP. And this was a joint work together with Pablo Spigliaris from our group. And here it comes. And from the very beginning, I would like to acknowledge his work because all the algorithms that have been implemented and all the results that have been computed and will be shown throughout this presentation have been generated by him. Okay, so then let me start with a general introduction. So we all know that NAD and NADP are two ubiquitous redox cofactors or coenzymes that occur in any type of living cells. So for example, here you see, let me switch on the pointer. We can see the central metabolism of E. coli, where you can find already 15 reactions using NAD or NADP. And in the genome scale model of E. coli, you will see that there are 128 reactions using NAD, 110 reactions using NADP, and 6 reactions using both. So those include, for example, the transhydrogenases. So NAD and NADP are chemically very similar molecules, so they differ only in one phosphate group, as shown here. So they have very similar chemical properties. In particular, they can accommodate 2 electrons together with 1 proton, yielding the reduced form NADH and NADPH. So with that, you might immediately ask the question, so why are there 2 pools of very similar redox cofactors? And the common view here is that simultaneous operation, that the 2 redox cofactor pools enable the simultaneous operation of oxidation and reduction reactions. So even though the standard redox potential is identical, the 2 pools have very different in vivo redox potentials because cells maintains the NAD pool mainly in the oxidized form, whereas the NADP pool is mainly in the reduced form. So this yields then these very different ratios of reduced to oxidized form of the redox cofactor. And with that, NAD can mainly function as redox, as an electron acceptor in catabolic reactions, which is then, so these reactions are then favored because we have high concentrations of NAD, whereas NADPH mainly serves as an electron donor in biosynthetic reactions in the anabolism. However, this is only half of the story because in the end, every NADH that is produced in the metabolism must be reoxidized to replenish the pool of NAD. And likewise, every NADP that is produced must be replenished in order to, or must be re-reduced in order to replenish the NADPH pool. And these reactions, of course, are then much less favored because you have then low concentrations of NADH and low concentrations of NADP. So with that, it might be not so certain whether 2 pools of redox cofactors are really advantageous for the cell. And a more general question here is what shapes the NAD and NADP reaction specificities in the network? So why is one reaction using NAD and the other one uses NADP? So our hypothesis here was that NAD and NADP reaction specificities are distributed such that the network-wide thermodynamic driving force for growth is optimized. So in order to tackle or to address this hypothesis, we will need different notions of thermodynamic driving forces, which I would like to explain in the following, using this simple example network here, where we have 2 parallel pathways, and we assume that we are given here the standard Gibbs-free energies of reactions. So now the driving force of a single reaction can be simply defined as the negative value of the Gibbs-free energy change of this reaction, and this can be computed here from the standard redox, from the standard Gibbs-free energy change, together with the concentrations of the involved metabolites. So now this can be extended to the driving force of a specific pathway. So here we say that the driving force of a pathway is simply the minimum driving force of all reactions involved in this pathway. Okay, so we compute the driving forces according to this formula, and then we take the minimum, and this is the driving force for pathway. So we can further extend this to the notion of maximum driving force introduced by Elliot Moore and co-workers, which turned out to be a really useful concept. So here the difference is that now the metabolite concentrations are not fixed. Instead, we are given feasible concentration ranges for these metabolites. And now we are looking for the metabolite concentrations that maximize the pathway driving force. That means we are looking for metabolite concentrations that maximize the minimum of all the driving forces of the involved reactions. So more recently, we extended this concept to go from a pathway to an entire network. We called this opt-MDF or MDF of a network. So here the situation is as follows. We have some flux constraints that we add. For example, here we demand that there should be a flux of 1 producing this metabolite here. And now we are looking for a pathway in a network that can produce this metabolite P with the highest MDF, right? So what we get in the end is a flux distribution R together with metabolite concentration ranges that fulfill these flux constraints and that have the highest MDF of all possible pathways in the network. So we have shown that this can be solved, or that this flux distribution together with the MDF can be found by mixed integer linear programming within a constraint-based metabolic model setup. So this is shown here. This is largely overlapping with thermodynamic flux balance analysis as has been developed by the group of Vasily. So here we have the standard constraint, the steady state constraints, we have flux bounds, we have the metabolite concentrations, and we have then the binary variables indicating which reactions are active in the flux distributions that we will compute. And so here are the driving forces, which can be computed from these variables. And B is then the minimum of all driving forces of the active reactions. So this here, this expression here ensures that we include here only the driving forces of the active reactions. And B is then the minimum of all driving forces of the active reactions, and this is maximized. Okay, so in this work, we even introduced another variant that we call sub-MDF or MDF of a subnetwork. It's basically the same as an MDF4 network, but here we define a subset of the reactions, in this case R1 and R8, which are here marked in red. And here we still want to find a flux distribution that fulfills a certain flux constraint, but then we only want to maximize the driving force of these two reactions, so only of a subset of the reactions, while ensuring that all the other involved reactions must be thermodynamically feasible. So again, so of course here in our context, the sub-MDF will mainly be used to compute the sub-MDF for the redox cofactor dependent reactions. So that's the reason why we introduced it. And we can compute the sub-MDF in a very similar way as we did here for the MDF. So there are only some minor modifications. So first of all, we now compute here the minimum of the driving forces of the reactions computed, which are contained here in the subset. And then we maximize for this subset-based minimum driving force. And of course, we still have to ensure that all other involved reactions must be thermodynamically feasible. So the driving force must be greater than 1. Okay, so with these notions now, we can ask the question, what NAD and NADP specificities maximize the MDF or sub-MDF for growth-related flux distributions in a given metabolic network? And how close is the Y-type specificity, for example, of E. coli, to this optimal specificity? So, and in order to address this question, we introduced here a framework, which we call TCODA, thermodynamic cofactor swapping analysis. And an important or necessary step that we do in a pre-processing step is a reconfiguration of a given stoichiometric or constant-based metabolic model. So for every reaction that involves a redox cofactor, We first split the reaction, if it is reversible, into two irreversible reactions. So this simplifies some computations. And then we introduce, for every reaction that involves the redox cofactor, a duplicate reaction where we swap the cofactor. So that means for every redox cofactor dependent reaction, we have now both variants in the model. So we apply this to E. coli, as you will see in the following, and we then consider growth on glucose under aerobic and anaerobic conditions. We use for the metabolite concentration ranges standard values that have been used also in many other applications. And standard Gibbs free energies of the reactions have been taken from the equilibrator. So, and in all the computations that we will do in the following, we consider now 4 different cofactor specificity scenarios. The first is the Y-type specificity. So this one uses the original NAD/NADP specificity, and we would leave out all the additionally introduced cofactor variant reactions. So we here use only the Y-type specificity. Then we look at the flexible specificity. So here the optimization can really select the NAD or NADP variant for each reaction. So that gives the optimization the highest flexibility. But importantly, for every optimization or for every solution it computes, it can only use one of those variants. So it's not possible to use both within one flux distributions. So it either has to take NADP dependent variant or the NAD dependent variant. So the next is the single cofactor pool. So here we allow only the NAD dependent reactions to be active. So the NADP dependent variants are not allowed. So this simulates the case where we have only one single cofactor. And finally, we have also generated random specificities, 1,000 random specificities, by a stochastic coin flip to select either NAD or NADP specificity for each reaction. And these random specificities can then be compared to the Y-type specificity. So, and now we can finally start doing these calculations. So what we did is we looked at these 4 specificity scenarios, and we computed for each of them the resulting MDF, first for aerobic conditions, and importantly, we looked here at different growth rates with a step size of 0.05, because as you can see here, for the highest growth rate, we have only 1 or 2 pathways available that would enable or support maximal biomass synthesis. And if you then decrease the growth rate, we get more and more feasible pathways. And then, of course, we can also get pathways with higher MDF. And for this reason, to really analyze also different growth rates here, we really looked at these different growth rates. And here you can now see the results. So let's first look at the flexible specificity, which is shown in green, in which, as expected, gives us the highest theoretical value for the MDF that we can get, because it can really switch between the different specificities. And what you can see is now that the Y-type specificity shown in black is really either close to it here for the maximum growth rate, or even identical to this maximum value that can be achieved by the flexible specificity. The single cofactor pool shown in red reaches significantly lower MDF values, as you can see. And this already indicates that really having 2 cofactor pools is really beneficial for the cell to reach higher thermodynamic potentials in the network. The random specificities are shown here in blue. So these are the 1,000 random specificities. And most of them are or reach smaller MDFs. As you can see here, but here's, for example, a single one that performs a bit better here for the highest growth rate. But most of them are with the MDF below the Y-type MDF value. And I can also tell you that most of these blue lines here are below the black and the green line. So they are slightly smaller MDF values. So that means in the end, most of the random solutions are worse than, or perform worse with respect to the MDF than the Y-type solution. So then we took the same for, or we did the same for the anaerobic growth conditions, and we got a similar result. Again, in green, you see the flexible specificity, and the Y-type specificity is close to it or even identical So here is one case where we have a slightly larger difference between these MDFs of the two specificity scenarios. But here for lower growth rates, we see that then the Y-type specificity again reaches the theoretical maximum. The single cofactor pool again gets much lower MDF values, and the random specificities are in most cases between the Y-type and the single cofactor specificity scenario. So then we did the same for the sub-MDF. Again, in those cases, we just want to maximize the thermodynamic potential or the thermodynamic driving force of the redox cofactor dependent reactions only. And in this case, you can see that the Y-type specificity even outperforms all these random specificities with respect to the sub-MDF value. And we get then similar results as for the MDF case. And here for the anaerobic conditions, we see that here it is even not much better than the single cofactor pool, but also here the flexible specificity sub-MDF value is significantly lower than for lower growth rates. But then for decreasing growth rates, we see that Y-type specificity is performing better than the random specificities, again getting close to the flexible specificity, though in those cases it doesn't reach these maximal theoretical values. Okay, so the first conclusion here is that the Y-type NAD and NADP specificity enables high thermodynamic potentials that are close to the theoretical maximum and significantly better than random specificity. So the next step, we then looked at the necessary swaps in order to reach for the Y-type specificity the theoretical maximal MDF and sub-MDF value of the flexible specificity. So here you see the number of swaps that are necessary. And of course, in many cases, we don't need to introduce any swap because the Y-type specificity reaches the maximal value. But in some cases, of course, we need to introduce swaps. In most of these cases, there are 2 or 3 or maybe 5 swaps necessary. But there's this singular case which corresponds to this growth rate scenario here, where we would require a larger number of swaps. In most cases, we need a handful of those swaps. And the following, I would like to show you 2 of those swaps, which occurred with a higher frequency and all these swaps computed, because this is quite insightful. So the first example here is a pyruvate dehydrogenase, which has a very negative standard Gibbs free energy, which indicates that this reaction is thermodynamically favored. And this reaction uses normally NAD in E. coli as a redox cofactor, as an electron acceptor. And our analysis now suggests that it might be useful to switch to NADP because synthesis of NADPH is thermodynamically unfavorable because the NADPH concentration is usually very high, as we will also see later on, also in the computation, not only in vivo, also here in silico. And then the switch actually suggests that maybe the synthesis of NADPH should be done in a reaction where you have a very negative standard Gibbs free energy in order to make this feasible. Another example is isocitrate dehydrogenase. This reaction has a positive standard Gibbs free energy change, and this means that this reaction is less thermodynamically favored. It's less feasible. And this one uses now NADP. And here the analysis suggests that maybe you should switch to NAD in order to get higher driving forces because, as we know, NAD is there in high concentrations, NADH in low concentrations. And with that, you get a thermodynamically more favorable reaction. But what I can tell you is that we did the same analysis also with acetate as a substrate, as I will show you later on. And then we see that switching to NAD is highly unfavorable when you use acetate as substrate. And this, of course, indicates that in order to fully understand the evolved specificities in a metabolic network, we would actually have to look at very different environmental conditions that are relevant for this. So the next thing that we analyze is whether we can confirm or whether we can also find in vivo trends of NAD and NADP concentration ratios in E. coli. So again, as already mentioned at the beginning, we know here that the redox state of the NADH is mainly in the oxidized form, meaning that this ratio here is low, whereas NADPH is there in high concentrations, meaning that the redox state here yields a very high ratio here for the NADPH and NADP ratio. And if you now take together these two ratios, we can form another ratio indicating, and this ratio should be far below 1, right? Because we take this ratio and relate it to this one, and this should be close to 0. So in E. coli, when you look at these measurements that have been provided here in this publication, you will see that this ratio is now 0.0053 in E. coli. And now we want to see whether we can find a similar value in the computations. So what we did is we took the Y-type specificity, and for each growth rate, we looked at the maximal MDF or maximal sub-MDF solution. And then we checked what are the feasible ranges for this ratio here. So in the following, when I talk about ratio, I always mean this ratio here. What are the feasible ranges of this ratio for the given growth rates? And what you can see is indeed for aerobic conditions here, for example, taking the MDF, we have a very tight range, which is indeed far below 1 and very close to 0. Also here for the maximum value, indicating that we can actually reproduce these results or reproduce these in vivo numbers that have been measured. And the same can also be seen with a sub-MDF. On the anaerobic conditions, at least for the low growth rate, you also have very tight ranges. So here the red dot even lies above the blue dot. Only for higher growth rates, you can see that larger ranges become possible. Also now a bit larger, but still also here in this case, they are still not far below 1, but at least below 1. So here we have a case where it's a bit closer getting to 1. Okay, so the conclusion here is that the qualitative trends of relative NAD and NADP concentration ranges can be predicted. So the next analysis that we did is now we want to see what would be the effect of adding now a third redox cofactor. And so that means for every reaction where we have the NAD and NADP dependent variant, we now introduce the third variant where we use then NADX as a third redox cofactor. There's one remaining degree of freedom, and this concerns the standard redox potential of this third redox couple that we introduce here. For NAD and NADP, we know that they have exactly the same standard redox potential. And for this NADX, now we considered 3 potential redox scenarios, redox potential scenarios. So the first is that we assume that we have the same standard redox potential as for NAD and NADP. So that would actually mimic the situation that we have a chemically similar molecule as we have for NAD and NADP. In the second scenario, we assume a more negative standard redox potential. And in the third scenario, we assume that we have a higher standard redox potential than for NAD and NADP. So with that, we then recalculated here the MDFs and sub-MDFs for aerobic and anaerobic conditions. In both cases, we have now 4. For MDF and sub-MDF, we have now 4 scenarios. So we recomputed that for the 2 cofactors and then for the 3 scenarios for the 3 cofactors. And what you can see for the MDF, we don't see any difference. We don't get any advantage with respect to MDF or sub-MDF. Maybe here in the anaerobic case, you see a very minor advantage when you use 3 cofactors for the case that you have a cofactor with a reduced standard redox potential, but this can hardly be seen. So, however, for the sub-MDF, we now see that we get significant improvements in the sub-MDF value for aerobic conditions if we have 3 cofactors and where the standard redox potential is more negative than for NAD and NADP. This is also advantageous for anaerobic conditions, although only for smaller growth rates. So for higher growth rates, we see only minor advantages in improving the sub-MDF value. But still, for aerobic conditions, we see really significant effects. So the conclusion here is that a third redox cofactor pool could be advantageous if it has a low standard redox potential. And it's quite interesting to see here that indeed several autotrophic organisms, like acetogens shown here, use ferredoxine. So here we have, for example, 5 reactions using ferredoxine as a third major redox cofactor in combination with NAD and NADP. And in fact, ferredoxine has a more negative standard redox potential than NAD and NADPH or NADP. And according to our computations, we believe that really gives those organisms additional degree of freedom to maintain their high thermodynamic driving forces in their really complicated redox metabolism. So here it might really pay off to have a third widely used redox cofactor. So as a last step, we did several robustness analyses in order to understand how far our assumptions or used parameters may affect the results. So in the first step, we tested the effect of introducing random variations in the standard chip 3 energies, because the standard chip 3 energies values, of course, have uncertainties. And we implemented this by random variations of the standard formation energies for each metabolite, which then yields consistent changes in the standard chip 3 energies of the reactions. And what you can see is here that, of course, now we get here variations in achieved MDF and sub-MDF values. But what you can see is that, again, the Y-type specificity here gets close to the theoretical maximum exhibited by the flexible specificity, and the single cofactor specificity really performs worse than the Y-type specificity that can use 2 redox cofactors. The same can be found then also here for anaerobic conditions with MDF, and then also here with the sub-MDF values we get very similar results. The next thing that we then varied are the metabolite concentration ranges. So here in the calculations I've shown before, we have used really broad ranges for the feasible metabolite concentrations. And here we use now measurements that have been provided here, again, in this paper here by Bennett et al. And we used these in vivo concentration values, which in the end are also ranges, but really tight ranges for the measured metabolite concentrations. And then we want to see what now the MDF or sub-MDF would be, and whether the Y-type specificity is really still advantageous. So we first computed that for the MDF, but what we found here, using these vivo concentrations, there's one single thermodynamic bottleneck in the network, which is not related to NAD or NADP dependent specificities, and therefore changing the NAD or NADP specificity would not change this MDF value. So there all these different specificities analyzed, including the random specificities, would yield the same MDF. So therefore, we now focus on the sub-MDF, and this is one example where having the sub-MDF is really useful, because we now want to see what is the maximum thermodynamic driving force in the network when focusing only on the redox cofactor dependent reactions. And again, what you can see is the Y-type specificity is by far better than single cofactor pool specificity, and better than almost all random specificities. It is even identical to the theoretical maximum here at maximum growth rate, but it is then a bit lower for lower growth rates. But here in this experiment, maybe that really what matters here really is the growth rate here, because the cells were grown with high growth rate. And also here the feasible concentration ratios for NAD and NADP, so the relative redox state of these 2 cofactors, again reflects what is then also measured here in this paper, that there is a very tight range indicating that the NADP pool is highly reduced state, and the NAD pool mainly in the oxidation. So the last thing that we then varied is to switch the substrate, as I've already mentioned before. So here we now use acetate instead of glucose as a substrate. In those cases, we can only consider aerobic growth because E. coli cannot grow on acetate under anaerobic conditions. And we then recomputed the MDF, the sub-MDF, and again, also here, these ratios, the relative ratios of NAD and NADP. And what you can see is, again, the Y-type specificity gets close to the theoretical maximum of the flexible specificity, and the single cofactor performs much worse. And the random specificities are in most cases below the Y-type specificity. And it's similar also here for the sub-MDF value, which also looks very similar to the glucose-based example. Okay, so with that, we can conclude that the results are really robust against different variations and the assumptions and these parameters. Okay, so that brings me to the conclusion. So we developed the TICOSA framework for analyzing thermodynamic effects of redox cofactor swaps. Our analysis indicates that evolution has shaped the NAD and NADP specificity of reactions in a way that enables high thermodynamic potentials in the metabolic network. And this result is also consistent to the work of Goldford and co-workers published last year, because they found that the redundancy of cofactors minimizes the enzyme demand in the network. And of course, this is consistent with our finding because higher thermodynamic driving forces require then less enzymes in order to establish certain fluxes. We used the MDF or sub-MDF as a measure for the network-wide thermodynamic potential. So here you can throw a caveat, because it is very likely that the cell is not in a state close to the computed MDF or sub-MDF value. The reason is that, of course, for example, enzyme kinetics will affect the feasible metabolite concentrations in the network, but enzyme kinetics has not been considered here in this frame. However, you should see that the higher the theoretical MDF that we computed here, the larger the thermodynamic flexibility of the network. That means the broader are the ranges of feasible metabolite concentrations in order to really let the network run a certain flux distribution. And therefore, we believe that the MDF still is a really useful measure also to analyze the feasibility of metabolic flux distributions. Yeah, and we believe that TICOSA can be used also for other species, and of course also for analyzing redundancy of other cofactor pairs, for example, ADP, GDP, and even for predicting optimal cofactor specificities, for example, for metabolic engineering, where you want to maximize the thermodynamic driving force along a pathway to the desired product. Okay, so with that, I would like to thank again Pavlos for doing much of the work I've shown here, and also Axel for some technical support and our entire group here in Magdeburg, and you for your attention.